Hi guys, welcome to a lesson of partial differential equation. So in this class, we are going to learn the applications of Laplace transforms for the partial differential equations, specifically the wave equation. So the idea is to use the Laplace transformations for the wave equation. And here's the problem is a homogeneous wave equation with the given boundary conditions and initial conditions. So here are the boundary conditions for this problem, and these are the initial conditions for the problem. So we are going to start with the equation 1. We will apply the transform on equation 1. So we know that the Laplace transform of dou I squared u over dou t squared is equals to s squared u minus s u of x comma 0 minus ut of x comma 0. All right, and then Laplace transform of dou I squared u over dou x squared is equals to d squared u over dx squared. So we are going to use these equations. Therefore, equation 1 implies that s squared u minus su x comma 0 minus ut x comma 0 is equals to 9 times d squared u over dx squared. U of x comma 0 is given 0, and ut of x comma 0 is also 0. Therefore, these both elements are 0. We are left with the equation s squared u is equals to 9d squared u over dx squared, and then d squared u over dx squared minus s squared over 9 times u is equals to 0. Now this is an ordinary differential equation. We can solve it easily. It's a homogeneous equation. Therefore, we'll construct the auxiliary equation and we'll find the roots for the equation. So the roots are plus minus s over 3. Therefore, the solution for this ordinary differential equation is u is equals to c1 e to the power s over 3x plus c2 times e to the power negative s over 3x. Now applying applying Laplace on boundary conditions before applying it to the equation 2, because this equation is in the mode of transform and we have u of x comma s. Therefore, we need to find u of x comma 0 and ut of x comma 0, right? So sorry, ux of 0 comma t, and this from here we can see that given initial conditions, here are the conditions ux comma 0 and utx comma 0 is equals to 0. So we will apply the transform on the conditions. Sorry, that were the initial conditions. We are going to apply the transform on boundary conditions here. These are the conditions. We'll write it again in the bottom. Ux 0 comma t is equals to 3 sine t. Here ux 0 comma t is equals to 3 sine t, and we are going to apply the Laplace transform on both sides. Therefore, this will become ux of 0 comma s, and applying transform on sine t, we know that the Laplace of sine at is equals to 1 over s squared plus a squared. So this is 3 over s squared plus 1. Now we'll apply the Laplace on the second boundary condition, that is u of x comma t is less than infinity when limit x tends to infinity, right? So we will apply the transform on the boundaries. Therefore, we know that if this is less than infinity, it means that it's equals to some constant. Therefore, u of x comma t is equals to some constant when x tends to infinity, right? So we can equate to some constant k, we assume that the value of constant is k, therefore u of infinity comma s will be equals to k over s, because the transform of k will be k over s because it's a constant, right? So now we'll apply, yes, we are going to apply these boundary conditions to the equation 2. Therefore, equation 2 implies ux of x comma s is equals to s over 3 c1 e to the power s over 3x minus s over 3 c2 times e to the power negative s over 3. We find the derivative here because the first boundary condition that is given is the derivative boundary condition, right? Now we can apply ux 0 comma s. So ux of 0 comma s will be s over 3 c1 minus s over 3 c2 is equals to 3 over s squared plus 1, right? So here is the equation. And now we'll apply the second boundary condition, that is u of infinity comma s, because we said that limit x tends to infinity. So we can write here x comma s, right? So it will be c1 e to the power infinity plus c2 to the power negative infinity is equals to k over s. E to the power negative infinity is 0. And then we can shift this e to the power infinity here in the denominator on the right hand side, and this is infinity, therefore anything over infinity is 0. So c1 is equals to 0, right? Now we'll put the value of c1, that is 0, in the equation here. So we will find the condition of a value of c1, sorry, using the boundary condition here. We already did c1 is 0 here. We can see if this is 0, therefore c2 is equals to implies that c2 is equals to negative 9 over s times s squared plus 1. So here we are going to use this negative 9 e to the power negative s over 3 times x over s times s squared plus 1. So this is our, this whole is our c2, and c2 times this function, right? So this is equation 3 now. Now we'll apply the inverse transform to find the value of u x comma t. So apply the transform on both sides. A Laplace inverse of ux comma s is equals to Laplace inverse of the function minus 9 e to the power negative s over 3x over s into s squared plus 1. So we can split this problem by using the partial fractions. So here we did, using the partial fractions, we find a, c, and b. Therefore, now it's easy to write this function in parts, right? So now it's easy to find the Laplace inverse transform. So the inverse transform of this function e to the power negative s over 3x over s will be the unit step function, because we know that the Laplace transform of e to the power negative as over s is equals to the unit step function, all right, or Heaviside function. So here this will be Heaviside of t minus x over 3 and minus, then this is s over s squared plus 1. So this s over s squared plus 1, the Laplace inverse of this function is cosine t. Therefore, this is multiplied by this e to the power negative s over 3x. Therefore, we will get a Heaviside function with cosine t shifted to cosine t minus x over 3. All right, this is a second shift theorem for Laplace transform. So in this way, we can get the solution for the problem in form of x comma t. So this is the final solution for our problem. So you can see how this Laplace transform works for the wave equation. Now let's move to another example. Here, the example is the equation utt is equals to 25 times uxx. The boundary conditions are given. Sorry, these are the initial conditions. We should write here ICs, and these are the two boundary conditions, right? Now, similarly, we'll apply the transform on the equation. We will get this d squared u over dx squared minus s squared over 25 times u. because the boundary conditions are, sorry, the initial conditions, that is u of x comma 0 and ut of x comma 0, both are given as 0. Right, therefore the equation will be simplified to this form. And then we can use the auxiliary equation because this is second order homogeneous ODE, so we can easily find the solution for this problem by finding the roots of the auxiliary equation. So the solution for ux comma s will be c1 e to the power s over 5x plus c2 times e to the power negative s over 5x. And then we will call it as equation 2. Now, applying the Laplace transform on the boundary condition. Similarly, the boundary condition is given as, this is t tends to, it's x tends to infinity, right? Not t, it's x tends to infinity. We can see in the problem here, it's x tend to infinity. So this is equals to k over s, because in the problem they said that limit x tends to infinity, u of x comma t is less than infinity. It means that it's equals to some constant, right? If it's less than infinity. So we'll apply the limits, we will get c1 is equals to 0. Again, we will apply the second boundary condition that is given ux 0 comma t is equals to 1 over 1 plus t squared. We want to find the Laplace transform of 1 over 1 plus t squared, but it's not too easy to find in this form. Therefore, we have to convert this to some other form. We will see how we will do that. Therefore, ux of x comma s is equals to negative s over 5. That equation 2 implies, because we partially differentiate equation 2, therefore we get as negative s over 5 c2 times e to the power negative 3 over 5, s over 5x. Then ux 0 comma s will be equals to negative s over 5 c2. That is equals to the Laplace transform of 1 over 1 plus t squared, because we said that this is the boundary condition. So now we will use some technique to find the Laplace of this function. So now we know that 1 plus 1 over 1 plus t squared can be written in the form 1 plus t squared power negative 1, which is equals to 1 minus t squared plus t power 4 minus t power 6, and so on. Therefore, it's easy to find the Laplace of this function now. So we will we want to find the Laplace of this function. So if we apply the Laplace on each element separately, so the Laplace of 1 will be 1 over s. Laplace of t squared will be 2 over s cubed. For this, it will be 4 factorial over s power 5, and so on. So here it's here is the Laplace transform of this function, right? So now we can easily write it. C2 is equals to negative 5 over s times the function, right? So again, we can multiply this s to the bracket, and we get this negative 5 times 1 over s squared minus 2 factorial over s power 4 plus 4 factorial over s power 6, and then so on, right? Now we just need to multiply this whole by e to the power negative s over 5x, because u of x comma s is equals to negative 5 over s times c2 times this function, that is e to the power negative 5 s over 5x, right? So it's multiplied by the bracket, and now what we get is this function. So we can apply the inverse transform to this function to find the function in form of u x comma t. Therefore, we applied the Laplace inverse here, negative 5 times the Laplace inverse on each element separately we can apply. So the Laplace of this function e to the power negative s over 5x or s squared will be given by the Heaviside function. Here we can see that. And again, this and this and so on. Therefore, we can use the Taylor series. Here we can see that Heaviside of t minus x over 5 is common, and then we will left with this in the bracket, which we can use the Taylor series. We know that the tangent inverse x is equals to x minus 1 over 3x cubed plus 1 over 5x5 minus 1 over 7x7 and so on. Therefore, instead of this whole function, we can write simply tan inverse t minus x over 5, right? So we will plug this value in the bracket and we will get the answer finally. That is u of x comma t is equals to -5 times tangent inverse t minus x over 5 times the heavy side of t minus x over 5. So hope you guys understand this lesson. These are very useful methods, the Laplace transforms, especially for some complex type of initial conditions. So hope you guys understood this problem. We will start some more topics in the next lesson, like the application of Fourier transforms for the wave equation. So goodbye.